Hardware Trojan is arguably the biggest concern for trusted IC design. Today we'll cover several practical techniques that help us to build trusted ICs by preventing or deterring hardware Trojan insertion. We start with pre-synthesis techniques. When we use third-party IPs, we want to ensure they don't have hardware Trojan or they are trusted before we can use them. So typically, there are two approaches to do this. First, we can turn this problem into a formal verification problem. We can verify whether the IP meets the specification or not. This can be done by doing property check, model check, or equivalence check. For example, when we want to check two combinational units, they are equivalent, F equal to G. The only thing we need to verify is the function fx times g prime x plus f prime x times gx will be a constant 0, where when we say times, this is a logical AND, when we say prime, this is the complement, when we say plus, that is the logical OR. This can be verified by the Boolean satisfiability solvers trying to verify this entity is unsatisfiable, which means it is always a 0. And for sequential components, we can do the finite state machine equivalence check. This work can be done with the concept called the product machine, which we will show on the next slides. On the other hand, instead of doing this as a formal verification problem, we can do this as a standard testing problem. We can test to make sure the delivered IP really meets all the specs. And the traditional design testing methods can be used. And more importantly, the hardware Trojan detection approaches we have just discussed can also be used here to ensure that the IPs do not have hardware Trojan. So now let's see what is the finite state machine equivalence and what is the product machine. Two finite state machines, they are said to be equivalent if and only if they give the same output on any input sequence. For example, consider this four-state state machine A, B, C, D with A as the starting state, and a three-state finite state machine X, Y, Z with Y as the starting state. We consider that on input 0, for both states, when the first one starts with A, it's going to output a 0. On the second state machine, start from Y, on input 0 is also output 0. So they agree on the output 0 and 0. When they receive 1 from the same starting state, Y, the second state machine, output a 1, and then the first state machine also output a 1. So they agree on their output. And for 2 bits input sequence, we have 4 different choices, 0, 0, 0, 1, 1, 0, and 1, 1. For example, if we receive a 2-bit input sequence 0, 1, on the first state machine, on 0, we output a 0, move to B. And then on the second bit 1, we follow this arc, we move to C and output a 0. So the overall output will be 0, 0. For the second state machine, starting from state Y, on the first input bit 0, we move to X and output a 0. On the second bit 1, we move to Z and output another 0. So the output will be 0, 0. Agree with the output from the first state machine. So by checking this one by one, we know that for these 2 state machines, any 2-bit input sequence, they also agree on each other. And we can keep on checking this until either they disagree on something, in that case, we call they are not equivalent, or eventually they become equivalent. Formally, this can be checked very easily or automatically by building the what people call the product machine. So consider the same 2 state machines, the 4 states A, B, C, D with starting state A, and the 3-state finite state machine X, Y, Z with starting state Y. So when we build the product machine, we first define their starting state. The starting state in the product machine will be any combination of the starting state from the first state machine and the second state machine. In this case, because each state has one starting state, so the product machine's starting state will be A and Y. If, for example, the first state machine has also A, B as a potential starting state, then for the product machine, it will have two starting states, A and Y, or B and Y. Let's come back to this example. So for the product machine, our initial state will be A and Y. On input 1, on the first part, A stays at A and output 1. And the second part, Y, stays at Y, output 1. So as a result, they move to the state, which is the same state AY, and they both output 1. So on input 0, A will move to B and output 0. Y will move to X and output 0. So they agree on their output, and then the next state will be the pair of B and X. So this will be a new state for the product machine. So we have to evaluate what will be the next state of this new state when we receive different input. So start with the new state BX. If the input is 1, so for B, it will move to C with output 0. For X, on input 1, it will move to Z with output 0. So again, they agree on their output, and then their next state will be a new state C and Z. So keep on this process, and then we check what happens when the input is 0. In this case, for B, when input is 0, it output 1, move to D. For X, when input is 0, it remains at X and output 1. So again, they agree on their output, and then their next state will be a new state D and X. So now we have two more new states, CZ and DX, and we're going to analyze them one by one by checking what will be their next state based on different input and whether they agree on their output or not. So eventually we'll stop when there is no new state can be produced. And during the way, they always agree on their output. So in this case, we see M1 and M2, these two state machines, they are equivalent. However, if at certain point the two state machines they disagree on their output, then by definition they are not equivalent, and then we can stop by claiming the two state machines they are not equivalent. So this is a very systematic approach, and it can be easily fully automated. Now let's go back to talk about hardware Trojan prevention. We finished about the pre-synthesis, so let's talk about the post-synthesis techniques. So there are several post-synthesis techniques when the chip is built with the layout is given. So first, we can do this, what we call the removal of dead spaces. So when the layout is given, there are white space, the space that are not utilized. And those are the potential spots for hardware Trojan insertions. So we can add dummy logic, trying to take away this white space to prevent direct hardware Trojan insertion. This is particularly effective to prevent big hardware Trojans. We can also do circuit obfuscation, trying to make reverse engineering harder, so the attackers will not be able to understand the circuit, and then it will be hard for them to insert a functional hardware Trojan. And we can also do shielding of the wires. This will be able to prevent the hardware Trojan based on electrical magnetic radiations. And because most of the hardware Trojans, they require a trigger signal, so we should pay special attention to interface protections. This interface includes the I/O pins of the system, the internal connections between modules, the power and the clock networks, and also the scan chains. So once we'll be able to control this, we can monitor this interface, and then whenever there is a suspicious communication, we can check whether these are required or they are the hardware Trojan triggering signal. So now let's talk about a couple of specific techniques to prevent hardware Trojan. The first one is called a rear event removal. And this is based on the observation that hardware Trojans use rear event as their triggers. If we can remove rear events, it will be easier to detect or activate the hardware Trojans. So there's an approach proposed by Salmi Taranipul and Plasquilic in 2009. And this motivational example shows the basic idea. What we have here is we have a hierarchical two-input AND gate. Assume that all the primary inputs are equally likely to be 0 or 1. And the two-input AND gate will give 1/4 chance produce a 1 and 3/4 of the chance produce a 0, because this will be 1 if and only if both signals will be 1. And then if we keep on proceeds this, for the second level AND gate to produce the 1, it requires both input here to be 1. So that is 1/4 times another quarter. So 1/16, it will be a 1. And similarly, we have an identical structure at the bottom half. So now for this two-input AND gate, for this one to be a 1, it will require both signals here and here to be 1. So this will be considered a rare event because the probability of this happening is 1/16 times 1/16, which is 1/256. So now let's see how we can remove this rare event, make it much more frequent. So the idea is try to add a flip-flop and a OR gate to change this wire connection with a logical connection here. So this is a scan flip-flop which we can control its input. So the output of the flip-flop or the content of the flip-flop will be equally likely to be 1 or 0. And then go through this OR gate. For this OR gate to be 0, we need both input signals to this OR gate to be 0, which is 15/16 and 1/2. So the chance for this to be 0 will be 15/32. And then the rest of the cases, it will be a 1. So now we consider this AND gate. For this one to be 1, it used to be a rare event, happens with 1/256. Now for this signal to be 1, we need this one to be 1, which happens with the chance slightly higher than 1/2, and then this one to be 1 happens with 1/16. So the product of this will be 17/512, which is about 8.5 times higher than 1/256. So this rare event will not be that rare anymore. So this can facilitate the hardware Trojan activation and the detection. And the next example is called shadow registers. So we have learned this technique called path delay based hardware Trojan detection. It's going to measure the path delay between two internal registers, and then trying to use this to detect whether a hardware Trojan was inserted or not. However, we mentioned the difficulty of this approach is sometimes we may not be able to measure the internal path delay. So the shadow register approach will be greatly facilitate the measuring of the internal path delay. So what we have here is we have the source register here, we have the destination register here. To measure the path delay here, it may not be easy because we may not be able to see these signals. So in this approach, we put a shadow register here, which has the same clock as the system clock. However, the phase of the clock might be different. So we call the clock 1 system clock. Clock 2 will be called a shadow clock, which is used to drive the shadow registers. So initially, the shadow register and the destination register will have the same phase. So they will have the same content, the same value. So when we do a comparison here, they will have the same value. And we can deliberately change the phase of the shadow clock, and then eventually they will become different. So, and this can be monitored through the result bit. When they become different, the comparison result will be different. So this significantly improved the observability or visibility of this internal path, and it can be used to facilitate the hardware Trojan detection. For details, we can check the paper by Lee and Locke in 2008. So there are many other approaches, and most of these are advanced research topics. So to end this discussion about hardware Trojan prevention or how to build trusted integrated circuits, we list several of these approaches. In 2009, Banga and Xiao proposed this approach called Vitamin, which is basically reverse logical gates, power supply, and ground. So this basically can turn a rare event into a frequently happening event, which can facilitate hardware Trojan detection or activation. And Gu, Qu, and Zhou in 2009 proposed an information hiding-based approach to build a trusted system. The basic idea here is they try to change the system specification deliberately, such that if a hardware Trojan is inserted, it will change the system's performance dramatically, and then this can be observed from the final system. In the same year, Chakrabarty and Bonnier proposed to use circuit obfuscation, trying to make the circuit much harder to be understood, and this will prevent, or in some sense deter, the hardware Trojan insertion. In 2010, Pochniak proposed methods how to build trusted circuits using untrusted CAD tools. So this is a very interesting approach, and in particular consider the fact most of the CAD tools will be considered untrusted. So this is a very interesting and very important topic. In 2011, Love, Jin, and Marquez proposed to use proof-carrying hardware to build intellectual properties that has the proof of trustworthiness, and then use this as the building block to build trusted integrated circuits. And more recently, Damba and Qu focused on finite state machine model to discuss how to build sequential systems with the trustworthiness. And their basic idea is by adding a control signal into the building block, which is a flip-flop.